Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is a little bit of a older work, but now we can reviving it again about solving the problem of mapping the reverse path in Traceroute. So
Okay, thanks G2. Thanks everybody for coming. I gave some of this talk years ago when I interviewed here, actually, possibly in the same, or at least in a very similar looking room. So there's kind of two things going on. One is I'm going to talk about the paper, which is from when I was at University of Washington in 2010. And so that's the set of authors down here. And we've just started reviving the project. And I'm only going to briefly touch on what we're doing with that, but I'm happy to answer questions about it. And that's the set of people up here. So Harsh has carried over. And please interrupt with questions at any time. So the motivating example that I'm going to give is from a Google paper that appeared at IMC in 2009. They found that 20% of client prefixes were experiencing really inflated network latencies, even though the clients had servers nearby. And so they built a system called YHI to debug these problems. I'm going to use one example that's in that paper as a motivating example. So in this case, there were clients in Taiwan, shown in the red box there. They were experiencing a network latency of 500 milliseconds. So this is enough to circle the equator twice. And so this system YHI set out to debug this problem. And of course, the first thing that someone like Google does to try to get good performance is to replicate servers at locations around the world and try to send the client to a nearby one. So one potential problem could be that the client was actually sent to a distant server. But they used server logs and verified that actually the clients were being served from a nearby server in Southeast Asia. So the next thing that you might think to investigate is the directness of the path from the server to the clients. And so they looked at trace routes from their data center, so looking to see if perhaps the path was really indirect. And using trace routes, they were actually able to verify that the forward path was quite direct. But most communication is two-way, including Google's, and most paths on the internet are asymmetric. And so it seems like there's probably a problem on the reverse path, but they have almost no visibility into it. So their conclusion was that to more precisely troubleshoot paths, they needed the ability to gather information about the reverse path back from clients to Google. In fact, this is a problem for more than just Google. In the past, they've built systems for geolocation, for monitoring internet outages, for predicting paths and internet performance. And all of these techniques take measurements as their input. But we could only see in one direction. And in each case, the biggest limitation that we had was the lack of reverse path information. It hurt their accuracy. And it's not just my systems. Many systems use sophisticated measurements, including things like netdiff from here. And they were all forced to assume symmetry and could immediately benefit from the ability to see reverse path information. So I've listed a few examples on the slides here, but really many systems that use Traceroute would benefit from reverse paths as well. There's been a widespread recognition of this limitation. So this is a quote from a January 2009 NANOG tutorial on troubleshooting paths with Traceroute. And this talk actually happens at most NANOG meetings still. So the number one go-to tool is Traceroute, but asymmetric paths are the number one plague of Traceroute, and that's because the reverse path itself is completely invisible. You can get a good idea about the problem when it's on the forward path, but you're basically flying blind if it's on the reverse path. That is our goal. We want to build a reverse Traceroute system that's deployable without requiring any new functionality from routers. So to show the setting, in this case, we control S. We can install software there. We don't control D. We want to be able to measure the reverse path from D back to S. And to bring this back to that Google example, in this case, S would be the data center, D would be the client. Of course, we can issue a forward traceroute. It gives us some information, but the path is probably asymmetric. We're not going to be able to just use TTL limiting like Traceroute does, because the destination is going to set the TTL to a normal value for the reply. Yeah?
Do you want us to board questions till the end? Or do you
No, please jump in.
Because one of the things that we've seen before here is that because of multi-bundling, sometimes even the forward path is you're on a one particular path of a multi-bundle route. And so there's some asymmetry, or there's some sort of other innovation, sorry, not innovation, there's some other sort of issue that could exist on one of like n paths. For example, it's the radix of paths that connect S to D could be higher than 1. This assumes 1, and it's true for everything, which may not be true going forward.
Yeah.
Certainly not true in our network, and neither it is true in Google's network.
Yeah, so we've looked a little bit at kind of how to incorporate our sorts of measurements into the type of like multipath measurement that's meant to uncover some things like that. Starting with Paris Traceroute, which was just looking at load balancers that showed up at the IP level, and now there's been kind of follow-on work looking at the issue where even within a given IP level path, you might get go through different links in a bundle. They might have really different performance, or they might have problems in them. We've done a little bit with this work, with extending it, with thinking about how to control which links we're seeing on the reverse path, and maybe how to expose them to kind of uncover differences along the reverse path. I don't have any particular slides on that today, but we're kind of in this process of just in the last couple of weeks starting to reboot the project, and that's one of the things we're hoping to kind of incorporate better going forward.
I think there are like multi-path traceroute, or some of the tools which do port and tuple hashing.
Yeah. So this is
figure out some of those things. I mean, we use those things today because we get some of the problems that you're talking about here are also visible in production today, where you have like one weird link inside a bundle going bad, and it's very hard to distinguish or to differentiate because 90% of the time it looks perfectly fine, except for 10% of the people who are not, and yeah.
Yeah. So the first place I saw this kind of multipath measurement was a tool called Paris Traceroute, which originally appeared at IMC 2006, I think, and then there were a series of follow-on papers. So one of the students on that is Italo, who is now faculty in Brazil and is working with me on the reverse traceroute project. So we're trying to kind of incorporate some of those ideas. Randy Bush also had a paper at IMC last year, I think, where that's where they looked at kind of even if you think you're getting the same path because it's the same IP level path, you would see really big performance differences within just kind of individual links in a bundle.
Correct.
And so they had a tool called Tokyo Ping, which is building off the Paris Traceroute. The same sort of idea. We've been looking at, I'm trying to think the setting we originally looked at this. Oh, I know what it was. So one issue you can get with this load balancing is if you have reverse path load balancing, but traceroute IP addresses are coming from the outgoing interfaces, then you can see what looks like varying forward paths, but it's really just the reverse path is being load balanced. So we're looking at kind of building tools that incorporate some of that information a little better. I don't have anything on that in the slides today, but we're trying to think about how to kind of control for those. So we need something other than TTL limiting if we're going to do it over the reverse path, because we're not going to be able to control what the client sets the TTL to, plus the error messages are going to go back to the destination. We don't control it. The next thing you might think to do is use other vantage points that we have access to. And in fact, we do have other vantage points around the world. So in my case, I use things like Planet Lab a lot. These aren't going to directly give us the path from D, but we're going to use them to get a view that's unavailable from S. And in fact, we're going to combine them to get a view that's unavailable from any particular vantage point. So what can we do with them? Well, first thing we can do is start issuing trace routes from them. Oh, I'm missing a slide there. But one of the sets of trace routes we can issue are the trace routes from all of our vantage points back to the source. And we're going to use these as a baseline that we can basically build off of. So the key idea that we're going to use is that internet routing is generally destination-based. And so from the perspective of a packet on the reverse path, destination-based routing means that it's routing towards S, and means that the next hop depends only on the destination, not on the source or where the packets come from so far. So this means that once we intersect one of these paths that we know about, we can assume that the rest of our path is going to be the same. In fact, destination-based routing actually gives us something even better than that. It means that we can build the path back incrementally. So if we somehow learn that the path from D goes through R1, now we just need to measure the path from R1 back to S, and we can ignore D. So this means we can stitch together the path a hop at a time. So destination-based routing doesn't always hold. We actually had a follow-up paper looking at kind of how often is it violated due to things like load balancing or tunneling. But it holds often enough that we found that it was actually safe to base a system around it. Just like Traceroute, there's going to be some caveats that you need to be aware of when you use this and assume this. But the results are still generally useful. So because of destination-based routing, we're able to learn the path goes through R1. Now we focus on measuring from R1. Let's say we somehow figure out that the path from R1 goes through R2 and R3. We then just need to measure back from R3. We somehow learn that the path from R3 goes to R4. We've now intersected a path we know about, and we can assume that we follow V1's path the rest of the way. And so we now stitch together the path. Of course, I left out a really key detail of how we actually get any of these segments. And basically what we need is something that can tell us a few hops at a time what IP addresses are on the reverse path.
So is it router-based or ASM?
So we're measuring at the IP level. So router-based with some aliasing going on and things like this. In terms of the impact of this destination-based assumption, part of the way we can get away with it is that even if you make some little errors within an AS, you'll often be right at the AS level. But we do measure everything at the IP level. So IP options are going to give us the tool that we need to measure a couple of these hops at a time. IP options, of course, are a built-in part of the internet protocol, but we're the first to use them to measure the reverse paths. The key is that unlike TTL, the destination is going to copy over the options into its reply if you ping it. And so the source can ping the destination with options set and get back the response, including the options. The first option that we're going to use is the record route option. So record route allocates space in the header of the packet for 9 IP addresses. If the destination is reached before all the slots fill up, the remaining slots can fill up on the reverse path. So to give you an example of that, if the paths look like this, then record route will give you these yellow hops, 5 along the forward path, the destination, and then the last 3 slots along the reverse path.
Ethan, have you tried asking people if there's flattened RR and other IP options on entry and exit?
Sorry, asking them if what?
I mean, have you tried experimenting with this? How? Some folks do squash record route.
Yeah.
Okay.
So I actually tried to put those results into my slides, and I couldn't find any recent ones that seemed worth including. But Rob Sherwood did a big study that actually kind of got me thinking about using options, where he looked at option support for record route across the internet, and that was like SIGCOMM 2008. We had a paper in IMC 2010 looking at timestamp option coverage across the internet. And I'm trying to get a student in class right now to look, because we've now accumulated a lot of data on record route coverage over time, and trying to get that student to look at how has it changed over time and what holes are there. Unfortunately, the student hasn't finished the project, so I don't have any great numbers on it. We've done measurements. We're hoping to redo coverage study. I also, I'm going to defer them until the end, but I have some extra slides if we have time that show things that you can do to help get better coverage where there's options problems. So for example, it's sometimes the case that the source might have options limited on its forward path, but the reverse path might be clear. And so in cases like that, you can have like this vantage point send the probe and spoof as the source, and so you'll miss that filter. And I have a graph at the end that I can show if you guys are interested, and there's time that kind of shows that that gets you a lot better coverage. There's other tricks you can do when there's limited option support in different ways, and a lot of the meat of the work in the paper was figuring out how to handle these different cases where people support options in different ways in order to get enough coverage that the system will work. And I have kind of what I would say in the end is there isn't going to be coverage some places. There's going to be filtering some places. The results that we had so far show that you can piece together enough coverage to have a useful system, even if it doesn't always work.
Do you know when it does not work?
Can you detect when it doesn't work?
I guess one of these, so maybe so I was trying to hold it, but since it's come up so last. So in my mind, I think one of the biggest difficulties in using network diagnostics tools of this ilk is like, it's hard to tell when they are wrong. Like, and it's almost like, I think tools that may give wrong information without telling you that this may be wrong are actually worse than no tools at all sometimes.
Yeah.
This is something kind of like I always wonder about, like some of the diagnostic work that I've done that uses machine learning or things like that, or even this thing where the answer may not be accurate and whatnot. How do you, in this context, how do you reason about correctness of the answer, since you are extrapolating from other factors?
Yeah, so our approach so far has been to include, so I mean, we're kind of just starting to get into it, but like what you're kind of hearing from this is we have to piece together different techniques in different places in order to deal with different issues that come up along the path. And so our approach so far has been to kind of label how we learn different pieces of information so that if you're, at least if you're looking at it as a user, you can understand this data came from this source and there are this caveats with that type of data. This other data came from this other source, and there are this other set of caveats, and you can reason about it like fairly similarly to how, you know, when I'm using Traceroute to understand some routes, I understand that there's caveats that I have to be aware of with Traceroute. The other thing that we didn't incorporate into the tool, but that we plan to when we're rebooting it now. So we had, so my student Toby, who's some of you know from his TCP work, before he started working on that, he looked at how often were these assumptions we were making violated. And the way we tested for that was to measure the same path in multiple ways and see when we got different answers. And so you can imagine building those tests into the tool so that you can trade off having extra probe overhead to remeasure the path multiple ways and then point out places where you're getting the same result in different ways, which gives you confidence, or where there's maybe divergence between the paths, which might mean that you might be a little bit more suspicious in those places.
Is there a way to like distinguish between false positive and false negative, like quartiles of under ROC curve, or has that effort been made? Is there a paper for both?
So we tried to tease out places. So the it'll come up later on in the evaluation, but the basic evaluation baseline we tried to go for is, do we get the same results as Traceroute or not? Because that's kind of what people are used to using. And we tried to tease out the different causes for differences between us and Traceroute. And so I'll get into that a little bit later on. Did that kind of answer your question, Ratul?
Yeah, I think you're hinting at things you might be able to do, but so I think that maybe if I will paraphrase your answer, it's like, which is the output of the tool needs to be carefully interpreted by a human. So which by itself, in the sense like I can put Traceroute in the context of a larger diagnostic system because its output can be trusted in some ways. And it'll be harder for me to put reverse Traceroute in an automated diagnostic system where this output of reverse Traceroute is one of the factors that go in because it needs to be interpreted by humans, at least as things stand.
So I think that you can put in, I think that we can tell, we have some pretty good information about when you should probably trust the tool and when you should probably not trust it. And the main thing is that, and again, this is kind of like jumping forward and backwards, but if we can't measure a particular hop, because none of our techniques work for that hop, we have to assume that particular hop is symmetric. This is kind of just our fallback. And what we found in a large-scale analysis is that if you only have to assume a hop of symmetry inside one AS, you don't really get screwed up. If you assume symmetry across an AS boundary, then you're probably in trouble. You kind of lose track of what's going on with the path. And so I think that in cases when we don't have to make those assumptions, it's fine to trust the tool at roughly the level of what you would trust Traceroute for, as long as you're aware that it's a slightly different set of caveats in terms of the types of confusing information it can give, just like Traceroute gives types of confusing information in some certain places. So I think we can flag the cases where you shouldn't trust it at that level and the cases when you should, and then it's safe to build something around it. Okay. So we've kind of jumped and already talked about some of the stuff in the future, but to come back to here, with Recordout, you would get those 3 hops. The problem is that the average path on the internet is like 15 hops in each direction, and so you usually won't be close enough to use Recordout. So what do we do in those cases? Well, in those cases, we can take advantage of the fact that some of our vantage points are able to source spoof, so they can send out packets with a source address set to something other than their own IP address. And what we're going to do is set it to S. So I already mentioned this in that other context of getting around filters, but for this 9-hop, 8-hop limitation, what we'll do is find a vantage point that's close to the destination, in this case V3, and we can have it send the Recordout probe to D. So when it gets to D, some number of the slots will be filled up, in this case 7. D will add itself in, but then it thinks that the packet came from S, so it's going to reply back to S. And we've now learned that R1 is on the reverse path from D back to S. And once we know this, we just need to determine the path from R1 back to S. So we can repeat the process. We find a vantage point that's close to R1. In this case, let's say V2 is. It can send the probe spoofing as S. It gets back. We've learned R2 and R3 are on the reverse path. But what do we do in cases where none of our vantage points are close enough to R3? Well, we still might have some idea of what the set of possible next hops are. And what we'll do is consult an internet atlas and figure out where we think options are for where it might go. So we might have observed paths like this in the past when we were just issuing trace routes. And so R4 and R5 are candidates for where this path might go. We need a way, given one of these candidate guesses, to verify whether or not it's on the path or not. And this is where we're going to use a different option, the IP timestamp option. We're going to use the pre-specified version of the IP timestamp option. And what this does is let you specify up to 4 IP addresses in the header of the packet. And each of them will record a timestamp if they're traversed in order. So this ordering property is what we're going to take advantage of. We're going to have S to test for R4. It's going to first ask for R3 timestamp, then ask for R4's timestamp. And that will force R4 to only fill out after R3 has filled out a timestamp, which means it must be on the reverse path. So in this case, we send this probe. R3 fills out a timestamp. If we get back a stamp for R4, we know it was on the path because the stamps are ordered. And we ask for it after R3. It has to be on the reverse path. In this case, let's say we do get back that stamp. So we now can assume that the path goes through R4. So we have a way now, if we have a guess, of testing that guess and verifying it. Now we've measured the path to R4.
You know that there was nothing in between?
So we don't know that. So we assume that if we observe them adjacent in a trace route before, and we observe R4 being on the reverse path now, that we can assume that it's going to be adjacent now. That's another potential source of error, although if they were adjacent in another path, it's pretty likely that they're probably adjacent again.
Dave, are you looking at it as adjacency from the IP level or
Yes.
adjacency from connectivity level? Because you could have, for example, IP things, but like say an ATM or a frame relay underlay with multiple hops in between.
There is certainly measurement, things like that could be hidden at the IP level.
That's my question.
Yeah, so we assume that because we observed them adjacent at the IP level before, that probably the path that has them both on it is going to be a direct path again, but if it wasn't, basically what we'd have is we'd be on a good path, but there should be some kind of ... between there. So now I've intersected the path from V1, and so we're just going to assume that we can piece it together like this. So there are kind of a number of key ideas that enable this. Of course, the goal was working without control of the destination, and so we're going to do this by using destination-based routing and multiple vantage points to stitch together the path incrementally. There are a bunch of other things you have to do to kind of get this to work well, and I'm going to defer you to the paper for learning about those. But as I mentioned to Vijay before, different routers process options in different ways. You have to account for this sort of variation. You have to deal with filters because some people are going to filter options, and of course some people filter source spoof probes. And then you want to make sure that it doesn't take tons and tons of measurements to do this. So we have some techniques for kind of correctly picking the right measurements that'll get us the most bang for the buck so we don't have to issue tons. Now, as I mentioned before, when none of the vantage points is able to measure a hop using any of the techniques, we're going to have to assume symmetry for that particular hop and then measure from there. So this means that the coverage and the accuracy are really tied to the set of vantage points that you have to use, and in particular to the ones that can spoof. So in the evaluation in our paper, which is what I'm going to talk about now, this was using Planet Lab and Measurement Lab sites that could spoof. And at that point, when we did the original study, about 90 sites allowed spoofing. That was about a third of the sites that existed. And then in the study, we measured back to Planet Lab sites. So we used Planet Lab sites as our sources and our vantage points. In the paper, we evaluate coverage and overhead. Here, I'm just going to talk about accuracy. And we'd really like our tool to be equivalent to what you would get if you had control of the destination and could just run Traceroute on it. People are kind of used to Traceroute, so it's nice if our output can look similar. We lack ground truth data of reverse paths for the entire internet, of course, otherwise we wouldn't need to build this. So what we're going to do is evaluate this in a controlled setting. We're going to use paths between Planet Lab nodes to let us compare a reverse traceroute to a direct traceroute. And when we measure the reverse traceroute, we're going to pretend that we don't actually control the destination. For the direct traceroute, of course, we do control it. And we had a similar study in the paper using Traceroute servers, public Traceroute servers, instead of Planet Lab nodes to get a little bit more path diversity, and the results were very similar. So it's not just Planet Lab biases that got us the results. So this graph is showing that comparison. On the x-axis, we have the fraction of the direct traceroute hops that we also saw using our reverse path measurements. And then it's a CDF of the paths that we looked over. So what you would be forced to do now is just to assume that the paths are symmetric. And this black line shows how well you do if you just assume and guess that the paths are symmetric. So you get a median of 38% of the hops right. The red line shows our system. So in the medium case, we got 87% of the hops that you would get if you were able to issue a direct traceroute. And then the benefit of the system is basically the shaded region here. Now, it can be hard to know if two hops are actually the same to make this path comparison because the routers have multiple interfaces and we might see different ones. So we might actually be doing better than this. Traceroute's generally going to give you the incoming interface. Record route will often give you the outgoing one. It can be hard to tie those two to each other.
Can you also be doing worse than assuming symmetric actually? So you say it's 38%, but couldn't it actually be doing better than that if you're counting something as being asymmetric just because the interface is?
So you're saying that just as our red line might look worse than it is, the black line also might look worse than it is?
Better.
The black line might look better. So the black line is our baseline comparison. We're trying to do better than the black line.
I'm saying that you're saying that it's wrong when you assume symmetric because you have some sort of ground truth, right?
Yeah.
In these tests. But that ground truth, are you assuming that the paths are different because you see different IPs in the hub?
Yeah, so
those might actually be the same.
right, so the black line might actually, the real black line might be somewhere further to the right because we might be saying it doesn't match, but it actually does match in some cases, is what you're saying. Yeah, so that's totally true. So we apply the same, we used IP aliasing data sets to try to identify all these cases. We used a number of techniques to try to pin them down. The techniques don't have complete coverage. And so in cases where they're missing coverage, we would count it as a miss both for us and for the guess forward line. So we're kind of in both cases, I think, conflating hops that are wrong with hops where we're right or guess forward is right, but we just don't know. And we tried to tease apart those two. Unfortunately, in this talk, I don't have the line for where the guess forward would move. It's in the paper. But basically what we did in those cases was instead of looking at things at the IP alias level, we tried to look at them at the POP level, where we were defining POP as basically all of the routers for a particular AS in a particular city with a particular airport code, basically. And so you can see for us in the median case, that gives us 100% accuracy. I don't have the line up here, but we have a similar line moving the guess forward according to POPs. I forget exactly what the numbers look like, but it's still a pretty big gap. And that's kind of the best we can do in terms of trying to account for these cases where it's right, but we don't realize it. Does that answer the question?
Yes.
So in the paper, we discuss other reasons why the paths might differ. But I think the main takeaway is that we might not always be 100% accurate. And sometimes we're not going to be able to give you the whole thing. But the differences are largely due to alias information, like I was just talking about, and then also to load balancing, which you can try to account for, like we were talking about with VJ before. So it gives you enough to I think that I came away feeling like we could trust the data in most cases and identify many of the cases when you wouldn't want to trust it. So I started out with the problem that Google is having with clients in Taiwan. And I'm going to just walk through an example of how you could use reverse traceroute to troubleshoot those sorts of problems. So in this case, we observed a round-trip latency of 150 milliseconds from a Planet Lab machine in Orlando to a network in Seattle. It wasn't UW affiliated, it just happened to be in Seattle. And that's about 2 or 3 times what you would expect. So currently, if you were trying to troubleshoot this, you might issue a forward traceroute and then look for circuitousness in the traceroute. And so that's the first thing we did. This is the traceroute from Florida to Seattle. And if you look at it, what happens is it starts in Florida, it goes up to DC, then it comes back down from DC to Florida, and then continues across the country. And so there is this big detour up to DC and back down to Florida, and that's explaining about half of the inflation. But it still seems like there's some problem on the reverse path. The forward path didn't explain all of it. And with existing tools, you'd really have no idea what was going on. So with reverse traceroute, we could actually just measure that path. So that's what this is. And if you look at this path, what's happening is it's starting in Seattle. It's going down to LA. Then it's going back up to Seattle and continuing across the country to Florida. And if you look a little bit closer at the hops, you can see that it's starting out in Seattle on Internap. It's going down to LA on Internap. Then it's switching over to Transit Rail, coming back up the coast on Transit Rail, and continuing across the country. And so one possible reason for this might be that Transit Rail and Internap only peer in LA, and the traffic had to go down there to get over a peering link. But I was able to verify with a traceroute from University of Washington that actually they peer here in Seattle as well. And so it appeared to be some sort of misconfiguration, out-of-date information. I actually was able to track down operators from both of those companies at Nanog when I was talking about this, and they verified that it was kind of an unintentional detour. So without access to both directions of the path, you really have no way to understand what's going on. You don't know who to contact to fix it. And with access to the information, even I, when I was in grad school, was able to actually track down people who were responsible for this routing and had the and were able to fix it. So that was one motivating example, but I do think that this information is potentially useful in many cases when you're using traceroute, and so I just wanted to walk through one other example of what you can use the information for. So there are many cases when you want link latency information when you're trying to understand routing, and the traditional technique to get in that would be to issue a forward traceroute and then assume that if you subtract the round trip time to A from the round trip time to B and divide by 2, you have some approximation of the AB link latency. Now, maybe you're going to have a filter to throw out obviously wrong values, but this is pretty commonly used. And this is going to be a good assumption if the reverse path is symmetric, like this case. But if the reverse path is asymmetric, you really don't know what you're getting when you subtract these latencies, because you could be following a completely different path from B back to S from the path from A back to S. And subtracting the round trip times doesn't necessarily mean anything. So the first thing that you can do with reverse traceroute is actually use it to tell which of these cases you're in. And in cases when you're able to find symmetric traversals, then you can safely use the subtracting technique to get good link latencies. So we've been able to solve these two because they're symmetric. But you can actually do better than that. You can throw in constraints from measurements to other destinations or from other sources and build up a system of constraints that says that the round trip time for any particular path has to equal the latency of the forward links plus the latency of the reverse links. And issue enough measurements, you can get enough constraints in the system to solve it.
So why wouldn't you, for such a thing, why wouldn't you directly use the atlas data you have? Like, for things like these, since you're merging information that was collected offline, so you're not actually getting real-time queue sizes. So you're basically getting maybe some low-pass filter on the queue size, or you're getting propagation delay.
Yes.
So I'm just thinking, if that's what the problem you want to solve, just use the atlas data and process it. Like, I don't need. What did reverse traceroute bring to the table here?
Yeah. So in our case, we were trying just to get propagation delay or some sort of measure of minimum latency over time. And the thing that you need reverse traceroute from is if these paths are asymmetric like this, I have no way of figuring out what the latency of AB is versus the latency to BC.
I was thinking the way you built your atlas, you already had all possible bag of trace routes you could conduct given your set of vantage points and destinations, right?
Yes.
So just process that data to do this, right?
Yes, so there might be some hops that don't appear on any trace routes from any of our vantage points and only appear on reverse paths. And I'll get to that. Actually, I have an example using the Sprint backbone in a second that will show how often we saw that. But basically, there's some links you're not going to observe at all. There's going to be some links that you don't have enough constraints to solve for. And so you need this to, first of all, tell which cases you're in. Second of all, build up enough constraints. So in this case, we used a measurement from V. Let's say it observed paths like this. We can then constrain these paths. And now we have enough constraints in the system to solve for AB. So we've solved for all the other links and can get that one. So yeah.
Let's see this.
OK, so we Sprint published their topology and had Traceroute server that let you issue pings between all of their routers, and so we were all their pops. So we were able to get a good ground truth understanding of their topology and the link latencies. And so we ran a comparison to see how accurate our technique was versus the technique where you just use trace routes and subtract adjacent hops. So the first issue is that with Traceroute alone, you might miss some of the paths. So there were 89 links in their topology. With Traceroute alone, from all of our vantage points, hundreds of Planet Lab vantage points, we only saw 61 of the links. With reverse Traceroute, we're able to see 79 of them. And then the graph shows the error and link latency estimation. So x-axis is error in milliseconds. Y-axis, it's the cumulative fraction of the links. And the red line is our technique. Blue line is if you use Traceroute. So in the median, mean, and worst case, we're doing 10 times better than Traceroute. Median and mean are both under a millisecond. So you can get a really good understanding of backbone link latencies using this constraint-based approach.
Really, I think to Russell's point, what you're seeing is backbone topological latencies, not link latencies. Right, because the link latencies are also dependent on instantaneous queue depth.
Yes, sorry, yeah. So propagation delay between pops is really what I mean.
Yes.
I haven't thought that much about it, but kind of what we were going for with this, we had a couple other techniques also to measure link latencies and one-way latencies that appeared in other papers. And the kind of goal for it was build an offline propagation delay map. And then that's potentially useful for comparing to live measurements and understanding current queuing, things like this. We haven't pursued that direction, but that was kind of what we were thinking with it. This would be not for live debugging, but for annotating a map offline, essentially, that you can then combine with live measurements.
It's useful for things like, for example, building global traffic management type solutions and annotating those, rather than any kind of like ISP would probably not use them.
Yes.
Internally.
Yeah. I don't think an ISP would want this for their own measurements. They don't need it. Yeah, exactly. And to maybe put the latencies in a little bit of a relative scale, the median actual link latency was 11 milliseconds. So a lot of links in the US were about 11 milliseconds. And the longest link in the data set was 97 milliseconds. So Traceroute in the median case is adding about 50% error. So most of that material was from the NSDI paper in 2010. I wanted to tell you a little bit about what we're doing with the project now. We've just started basically rebooting it. It's been shut down for a while. We're trying to build a better version of it. The goal is to have an open system that people, researchers, and operators can actually plug into, use our vantage points to make measurements, and to have an operational staff to help support that. So we're building a client source code that you can use to plug into the system. We're adding vantage points. So we used Measurement Lab in our original measurements. So everybody familiar with Measurement Lab? So it's a test bed that Google and some other people started that's meant to expose information about broadband home networks, essentially. It's basically data. It's supposed to give transparency into edge networks, basically, to give the consumers a better idea of what's going on with their traffic.
Sure, the sites are not inside homes or residential ISPs. The
No.
lab sites are still very much like server-centric.
yes.
Yes, exactly. But the nice thing from our perspective is we don't actually want vantage points in the home networks. What we want is vantage points that are in well-peered locations so that they're close to lots of things for doing our spoofed measurements. And so from our perspective, Measurement Lab is really well located. So it's at major pops, basically.
Intersection, the peering.
But like, I think the thing about reverse tracer in general, like I think you want to continuously keep calibrating the system. Like your original calibration and accuracy measurements was done on Planet Lab with some augmentation, like you mentioned.
Yep.
Most of the times, like people like us, we are interested in like users inside homes. So from that perspective, I would say, and you can correct me if wrong, reverse traceroute is completely uncalibrated.
So it's true that we haven't done a validation study in that sort of context.
Well, I'm not sure we actually really need to here, right? So the way I'm thinking of this is, I'm assuming, Ethan, you'll be publishing, for example, what your data structures are for your annotation and the maps. So we can use those data structures, map them with real user measurements and stuff that Chad's team is doing on the client side. Then you'll actually have an idea of what's happening. Because the client side is blind, right? Client side will go from measurements from the client to the server, but in between it goes opaque. And you move the next layer down.
Actually, a simpler problem. I think that's useful. I was talking so there's some coverage and accuracy numbers Ethan has based on what he's built. Those numbers are driven by where he could get the sites. Now the data we're interested in is around like people sitting in homes and trying to reach Microsoft or Google or whatnot. Like those set of clients may have completely different characteristics with respect to their routing, where reverse traceroute tricks may or may not work. So
that would be mostly in the CRAN type stuff, right? Which is the local access networks.
Yeah.
Access networks are going to be like, from a measurement perspective, are going to be, for example, interleaving in DSL is adding on like 20 milliseconds to whatever you're doing.
even if you forget performance, if you just wasn't a path, let's say, I think it would be good to know. Okay, I think here's what I'm asking, like what do you need to do calibration for home users? Because that's where I think content provider is interested in. So
he has those ripe nodes, right?
What?
He has those ripe nodes, and a large number of them are going to be.
Actually, that's a good point. So So that would be interesting to see. Okay, so that.
Yeah, so this is one thing that we're working on right now is incorporating Ripe Atlas. So Ripe Atlas is these little USB Ethernet dongles, and they've kind of very quickly got a very large deployment. So they have 7,000 nodes in thousands of ISPs. Most of them are in access ISPs. And so right now we're working on incorporating those into our system as traceroute vantage points, essentially, but also as potentially a validation data set that has more access measurements. So a couple things to think about in terms of coverage. One is that usually what we're trying to do is measure a couple hops until we intersect a path that we already know about. And so you don't need to measure across really long distances usually. The other is, I don't know, but my instinct would be that most home users' paths are symmetric for the first couple hops. Like you're not going to have lots of asymmetry for the pop where your traffic enters.
The data we've seen, I think for large residential ISPs, they could be doing weird things with.
So
you go blind inside, let's say Comcast. Comcast is a large residential ISP, and I don't know to what extent symmetry would hold in there.
So not across.
And those, like at least large residential ISPs, my understanding is they do a lot of tinkering with how traffic flows through the network, and that is what leads to asymmetry.
Yeah. So I would need to look back at measurements to see which of those we have good visibility into, but at least in many cases, if it's that large of, like someone like AT&T who has a globally distributed backbone, like in those cases we can get pretty reasonable coverage in a lot of time.
But the residential ASNs are different, so I don't know if.
Anyway, it's worth looking into. I haven't looked at it, so I'll stop.
It might be a good source, and I'd be very curious if you went back and did the same analysis using.
So I imagine that once we have the system fully up and running, we'll do that analysis. We're also trying to add in optimizations to make the system more efficient at scale. So some kind of obvious directions that we've been pursuing is caching of partial measurements and figuring out how long you can safely cache partial measurements for and how you can either use those to construct a path because you believe that the path hasn't changed, or use them to give you hints on what measurements you should issue so that you can very quickly refresh a path rather than having to measure it from scratch. We're also working on inferring rate limits at routers to our different types of probes so that we can kind of safely push the limit without kind of triggering a situation where our probes are getting ignored. And kind of doing smart centralized scheduling. So the piece that we're doing right now with Ripe Atlas is trying to build a system that smartly selects what trace routes to issue that are likely to kind of help you with a particular query that you're working on. So there are, thousands and thousands of Ripe nodes. We can't constantly be issuing measurements from them to every destination in the world. And so we have kind of a prediction engine that can smartly allocate our budget to try to get the most use out of the Ripe nodes. So this lack of reverse path information was identified as a key limitation by Google in their IMC paper, by operators, by researchers. You really had no way to get this information, and so anyone who cared about internet routing was really only seeing half of the information. We built this reverse traceroute system to try to give us richer information and address this key limitation in traceroute. I had this example of using it to debug performance problems. We hope that it's also useful in a range of other settings, and kind of like to think that most settings when you're using traceroute, you could get useful addition from using reverse traceroute as well. We can essentially tell you how anyone gets to you. And so our goal is to really build this into a scalable system that can support community measurements and not just have it as a little thing that I run on my own desk. Happy to take more questions.
Since you said you're rebooting it and looking to add new things in the future,
yes.
I'm going to ask you about two things, which you may not have thought about yet. That's fine, but maybe a request for doing things. Number one is IPv6, right? As we start to see more traffic shift to IPv6. It used to be the case that you could get reverse trace route very easily in the IPv6 because there was the routing header that you could use to do a round trip and record routes and so on. But since that was deprecated, you can't. And so it seems to me like some of your same techniques might translate, but since you don't have IP options, maybe you need to find other equivalents. And so that would be the first request, because I think that would be an increasing need going forward.
Yeah, it sounds like a great idea. Kind of level that I've gotten to is exactly what you say, which is like there used to be support for it. There's also a proposal for record route where you could tell it which hop to turn on, which would have been really useful. Again, deprecated.
What we want right now is how can you do it in today's internet rather than what might.
Yeah. So I haven't looked into it. It's a great question, and we're moving towards. I kind of have this coupled with a BGP testbed that we have, and we're moving towards IPv6 support for the BGP testbed, and so it's a great thing for us to think about going forward in this. I haven't looked into it yet, though.
So the second thing is, as people start deploying things like carrier-grade NATs at the edge of large ISPs, can you use piecing together two things? It gets to, with inside the carrier-grade NAT, it might be symmetric, but it's the same point as we were talking about before, is it might actually not for these very large ISPs and so on. So if you can do something there, it might be part of the same work as we're talking about there. And then if you can do work on both of those, just to stretch goal, you can put them together and try to go through a NAT 6.4. And do a trace route through that, which would be the ultimate. Right?
Yeah, that sounds interesting. Like you hypothesized, carrier-grade NAT, also not something we've looked into a ton. And kind of all these cases, I think it's pretty interesting to try to figure out new techniques that you can use to try to get some visibility, like into tunnels and behind NATs and things like this. I don't have great answers on what exactly those techniques are.
I would think would be a great topic for future papers. Right?
Sounds perfect. I agree. Those are all interesting. Any other questions or any more questions on some of the things like the filtering that I can actually show that result if you want.
Okay, so yes, I think we should, but I'm looking at it operationalizing some of this, right? So the two things normally come to mind. Three things. First one is, how are you funded for this? B, what is the long-term context if we, for example, ask the global load balancing team, Chad's team here, to build something that depends on this? What happens if you get bored or somebody gets bored? How do you productionize that particular component? Because the system here would help. It's not the final, but it would help in improving our visibility. And the third one is like if you open source it or plan to open the system, is there a mechanism for constant care and feeding of this or some sort of other, I've seen grad school code, right?
Yeah.
So how does this work in production environments? So
this is kind of what we're trying to answer right now. So the previous funding was NSF research funding, Google research funding. The new funding is NSF community research infrastructure funding. So it's designed to build infrastructure. We just got that funding and just put out an ad for a full-time developer on the project. And then have funding for operational support staff for a couple years on this combined with the BGP testbed. But we also want to, in that time, start thinking about how to have a long-term home for it that shouldn't be grad students, because that's not sustainable. We're in this new version of it, we're planning on building in more automated recovery, more automated monitoring, things like this, and we'll have full-time staff. But we want to open source the code for sure. We want to find some way for this to live long term. Right now, we have a 3-year plan for it living, but I'd love to chat more about kind of ways of making sure that it lives past that. Kind of where we're at right now is like, as a grad student, I was able to kind of maintain a version that we could use at University of Washington for 2 years, but then I got too busy with other things, and that model is clearly not going to work.
Most of your infrastructure is based on like Planet Lab, which is not open to the industry at all. So how can we utilize those infrastructure to build our own production system?
You're not currently planning to use Planet Lab for V2, right? It was right. Measurement lab and
so it's a little bit up in the air if we're using Planet Lab or not. It's gonna.
I think the important point to Yingying's point is like the users of reverse traceroute system don't need to use Planet Lab directly.
Yeah. So the model is we have a live distributed system. You have a piece of client code that can hook into our distributed system, make a request to it. It will orchestrate your measurements with Planet Lab, but you don't need to directly access Planet Lab. So that's the direct answer to your question. In terms of whether or not we're using Planet Lab going forward, we're kind of assessing Planet Lab's long-term health at the moment and trying to figure this out, and also assessing how much benefit it provides now that we have Measurement Lab has extended a lot in the last 4 years, and we're being incorporated as a core service in Measurement Lab now, and now that Ripe Atlas has provided some of the diversity. So we're going to assess whether or not we still need it.
So like
what's the longevity of the Ripe Atlas? Because Matt, we give them a little bit of money. Their communication model is like there is this one person who sometimes answers emails. Right. I mean, that's the.
Yeah, it's a good question. So Ripe Atlas, years ago, I think even possibly before I did reverse traceroute, maybe from Hubble, they contacted Arvin and me and asked if we wanted to help them kind of design this system that they were thinking about at that point. And at that point, they went to their body, like we had a proposal, they went to the body and it didn't get funded. And we dropped off the project, I didn't hear about it, and then next thing I knew, they had hundreds or thousands of nodes. So they are reliant on their members to fund the project. That's a really good question, but I don't know like how long it's funded for right now, what their plan is. They've done a good job with every other system that I can think of that they had. Of once it was funded, it continued to operate. Like Ripe Riz, their BGP collector, has been around forever.
Are you exploring the FCC SAMNOS stuff? Like that could be another kind of source of funding. FCC's.
Yeah.
Hopefully they won't move away. Like because NSF, I think you're right. NSF is not designed to fund infrastructure.
So for Sam knows, if Matt wasn't so busy with you guys, maybe he would have made progress on that project. He and Toby are supposedly, like, they approved a project proposal from us, and just nobody's had time to work on it. It was Matt and Toby, but they're both, like, Toby lives at Google and Matt lives here.
Important stuff, so you should use Toby.
Toby's doing very important stuff at Google. We hear that, okay.
Yeah, and actually his new stuff it'd be interesting to get your feedback on it.
So like, is it possible that, and I've talked to Ratul about it in the past, that we have development resource in-house and we use that to like, a version of your code lives in our organization and we build it and we kind of go back and forth and
Yeah, I'd love to figure out a good model for this. A big problem for us is, we're not a software engineering shop. Like, it's, when we had students work on it, it works for a while and then pieces die. Right now we're trying to hire a developer, but that's not something we have experience with, so we'd love to find ways to do this.
For us, like the hard part is fair the continuity of it, like kind of, have it, keep the business running.
If we can find a good model for it, I'd love to do that.
So you mentioned there's another infrastructure, like you use tens of exchange point location to do the reverse traceroute. So how is that open to everyone, or is it just something that you deploy the server there?
So in terms of our BGP infrastructure that we have?
No,
or
go to the previous slides. You mentioned there's
Oops,
another.
This one?
Yeah.
Oh, yeah, sorry. Yeah, right. I didn't mention, I forgot that in my mind, that said Planet Lab still. That was my answer to your question. That said Planet Lab until this morning. Yeah, so we have this BGP testbed that's now called Peering. It used to be called Transit Portal. And what we have there is, I have a /19 prefix and just adding a /22, and I have an ASN, and we're building basically a research ISP that researchers can use if they want to do interdomain routing research and do BGP research. So we peer currently with hundreds of real ISPs, including Microsoft. Hope is by the end of the year it'll be thousands, and we're putting routers into Internet Exchange points that run our software. So right now we're in Amsterdam Internet Exchange, which is one of the biggest couple ones, and we're in a smaller one, and we're kind of looking to expand that over the spring semester. And so those routers that we have for that will also be running reverse traceroute code because they're really close to a lot of networks. They have like hundreds of peers, and so they're good as vantage points. In terms of using the Internet Exchange access, again, we're building a community testbed there, and so we're accepting proposals from people who want to use it. That's what I gave a talk on Friday at UW about that.
Like open that for public use, like we do a traceroute from the exchange point server that you have located there. So
in terms of traceroute experiments with that, the plan is to expose it as part of the reverse traceroute system. I hadn't thought at all about exposing direct traceroutes from it. A lot of the same exchange points are going to already have traceroute servers. AMZIX, I'm pretty sure, does at least. So the two ways, at least so far, I'd thought about exposing it was, one, it'll be part of the reverse traceroute. So if you hook into that, one of the vantage points that might get used to make some of your measurements might be at an exchange point. And then two, if you're running BGP experiments, we accept proposals for our BGP testbed. OK. And I don't know, Vijay, do you want to see the results showing the filtering that you were asking about?
Yeah, that would be very helpful.
Figure out how I cut ahead.
The reason I'm asking for that is that if you can tie it to per AS, and
Yeah.
expose that as a data structure, we can then say, okay, well, for these ASs, move the error bar to useless,
Yep.
and for the others,
Yep.
use them.
This is exactly what a student was doing for a class project this semester, but he didn't finish it. But I agree that that's how you want. You want to know, like, here I should look, here I shouldn't.
What kind of student are you guys?
I don't know. He was in the theory group, so maybe this was a little bit too close to the. So to give just some ideas on IP options support, I couldn't find any great poll numbers from Rob's papers, but he has this SIGCOMM.
Things are so old.
Yeah, it's true.
Then don't even bother.
Okay. So I'll skip this. But so this is showing. This is again old data, but showing the fact that you can use vantage points to get around filtering in a lot of cases. So the scenario here is you're trying to measure from D back to S again. When S sends the options probes, they're filtered. How often can we find another vantage point that can get around that filter and still measure the reverse path? And so this is showing over 1,000 destinations that responded to options from somewhere. How many responded if you send a direct probe, and how many responded if you bounce the probe like this? So the white, and then this is just showing for Planet Lab nodes. So the white is how much they could get on their own. The red is how much they could get with help. And so you can see in a lot of cases, using other vantage points to get you around filters actually is a really big benefit.
This isn't as bad as I was thinking. I thought this was going to be pretty bad because it might be also useful to bring up like per AS and then say which ones. I mean, if you can have like a bunch of small ASs who are okay with spoofing because they don't know any better, right? I mean, this is the clown category. And then there are some larger ones who may be, and they're the thing is how much of the path or the customer base is covered by people that squash and how much is covered by people that don't. Right? This now it's all equal weighing.
Yep.
Yes.
Yep. Yeah. I agree. I don't have results that directly look at that here, but certainly that's kind of.
We can just eyeball it, and I can tell you.
Yeah, it's certainly what you want to think about. The nice thing is that, in general, the closer you are to the core, the less likely you are to be filtered, just because it's really hard to set up the filters. And so, last time I checked, which is maybe last year, all of the measurement lab nodes except for one could spoof, whereas the Planet Lab percentage is much lower. And the other thing is, I mean, we're spoofing, but it's in this very restricted way that's safe, where we only ever spoof as one of our other vantage points. And so, like when I initially talked about this at Google, they didn't even really consider this spoofing, because really what you have is one of your vantage points pretending to be another one of yours. They're both Microsoft IPs. That's not spoofing. That's just like any casting the address. Like it's in some sense it's more similar to that. And So if we have kind of a real deployed infrastructure that's not just me piecing together Planet Lab, I can imagine that it might end up working out more like that, where this range of IP addresses is actually a perfectly valid set of IP addresses to source from here. It's not spoofing arbitrary things. And like at USC, we were able to set up kind of that sort of whatever, the opposite of filtering. ACL is to like let us do that 3 ISPs up from us so that we can do these sorts of measurements.
Quite interesting. But yeah,
Yeah.
that's actually very cool.
Any other questions? Okay, thanks.